So in this lesson, we're going to launch right into thinking about fuels by addressing what I would say is the most obvious question: what is a fuel? And in order to define what a fuel is, you're going to see that we need to distinguish between so-called physical and chemical changes. So there are two major topics that you're going to see in this lesson. That is, what is a fuel and what distinguishes physical and chemical changes. So from a chemical perspective, a fuel is a material that can react with another substance to release chemical or nuclear energy in order to do heat or work. Now, I told you in our introduction that heat and work are specific ideas in thermodynamics. We're not going to do that yet. For the moment, we're going to focus specifically on what a fuel is and what a reaction is. So in this particular lesson, your goal is to be able to understand what is a chemical reaction and what is not. Because unless you understand what a reaction is, you can't identify whether something has undergone a reaction, and you can't understand what a fuel is if you don't know what reaction it can undergo. So before we look at some examples of chemical reactions, let's first define what a chemical reaction is not. So let's take a look at this image here on the left-hand side. What you see is a carafe of water boiling on a stove. You can see that it's boiling because we see little bubbles in it. If camera could take better pictures, we'd see this steam up here, and we'd see water down here. This is, of course, liquid water. Steam is, of course, gaseous water. So this is an image of water boiling on a stove. Is this an image of a chemical reaction? No, absolutely not. Why not? Well, what happens when water boils? We take liquid water, which you probably already know is represented by the chemical formula, the molecular chemical formula H2O, so two hydrogens bound to a single oxygen atom. So we have that liquid water, we heat it up until it has enough energy to become a gas. But when it becomes gas, is it still water? Yes, it's still water. Each molecule in the liquid water consists of an oxygen bound to two hydrogens. Each molecule in the steam water also consists of an oxygen bound to two hydrogen atoms. The chemical identity of the water is not changed at all by boiling it, by transforming it from a liquid into a gas. And so this is not a chemical change. A chemical change is one in which a substance is changed from one chemical thing to a different chemical thing. In water, we're just changing H2O, the water molecules, from being liquid to being gas. Why are water molecules liquid sometimes and gas others? We'll come back to that in this lesson. But it's important because it's important to recognize that we can have water molecules as a liquid and water molecules as a gas, and that's not a conundrum in any way. So the important point is that in this boiling of water, no chemical bonds are broken. All of the chemical bonds that exist in the water, in the liquid water, still exist in the gaseous water. So we call this a physical change. This is a physical change. We call it a physical change because it's what we call a state change, a change of state. It's a change in which the form of matter, the state of matter, goes from being one thing, a liquid, to a different state, gas. So just to review some concepts that I'm sure you've seen in other places, the various states of matter that we know are solids, liquids, and gases. So here on the left side, we see a picture of rocks. These are solids. Here in the middle, we see a droplet of water springing up off of a surface. This is a liquid. And then here in this bottle on the right, this is actually a sample of gaseous chlorine gas. So the gas sample expands to fill the entire bottle. This is an example of a gas. So each of these is a state of matter. And if we boil the liquid to transform it into a gas, that's a state change. That's a physical change. Or if we take a rock, say a bit of something, and we melt it, so ice, and we melt it into water, that's a state change from solid to liquid. And again, that's a physical change, not a chemical change. So a change of state is simply a change from one form of matter to another. I've given you examples of going from lower energy states to higher energy states, solid to liquid, liquid to gas. But you can also go the other way. If you condense water from the atmosphere to make ice, that's also a state change. It's not a chemical change because no bonds are broken, no chemical transformations happen. A chemical change, on the other hand, is different. So in this figure here on the left, we see burning wood. Is this an example of a chemical or physical change? The answer is, in this case, this is a chemical change, because what we start with in the wood before we set it on fire is a collection of various organic molecules. And then during burning, those various organic molecules react with oxygen in the air, and they form carbon dioxide. That's actually a typo. I should say CO2. They form carbon dioxide and water. So in the beginning, we've got bonds between various carbon atoms and other things, but in the end, there are no bonds between carbon atoms. So bonds are actually broken during this reaction, and new ones are formed. That's the definition of a chemical change. So burning of wood is an example of a chemical change. Let's take a look at another example. This is an example of fireworks exploding. Do you think this is a chemical or a physical change? Well, exploding fireworks is very much like burning of wood. It's a chemical change. The chemicals in the fireworks react with something when they're set off, usually oxygen, and you get an explosive reaction that generates the light and the heat and the sound and all of those things. It's usually various components to get different parts. But the firework, the chemical composition of the firework is actually changed by the reaction. So this is an example of a chemical change. Now, would you call fireworks fuels? I suspect the answer is no. But why not? Why are fireworks not typically thought of as fuels? Would you call wood a fuel? Yes, you probably would. What is inherently the difference between the reaction of wood burning and fireworks burning? Well, the difference is that the reaction of fireworks is what we would describe as explosive. It's a burst of intensity, a lot of energy released all at once. And so it's actually quite difficult in those circumstances to be able to harness that energy to efficiently do work. And that's why we don't typically think of fireworks as fuels. And so here's a really important notion of what a fuel is. A fuel is intimately connected to the idea of doing work. It's not sufficient to just be a chemical change. It's not even sufficient to be a chemical change that produces energy. That energy needs to be harnessable in some convenient fashion in order to actually do something, for us to think of a substance as a fuel. Now, we talked a few moments ago about physical changes, and so it's worth noticing that fuels can exist in any of the three different states of matter. So this image, for example, shows a collection of tea lights on fire. Tea lights use paraffin wax as a fuel. Paraffin wax is actually a solid. When you buy a tea light, you've got a sort of waxy, solid substance in the bottom of the tea light that stays solid until you catch it on fire, it gets hot, and then of course it melts. So fuels like paraffin or coal or wood, these are solids. And solids are defined specifically by a fixed shape and a volume. And you've learned in the previous lessons that solids are largely held together by bonding between the atoms and also by intermolecular forces. So the energies of the interactions in a solid are such that those atoms are held very tightly in place, so that the atoms don't have translational energy to be able to go wherever they would like. On the other hand, you almost certainly know that the fuel used to power an automobile is liquid hydrocarbons. Petrol, benzene, gasoline, whatever it's called where you live. Liquids are a different state of matter that have a fixed volume like solids, but they don't have a definite shape. When you take a liquid and you put it into a container, it then conforms to the container to take on the shape of the container. So we recognize immediately that the properties of liquid are different from the properties of solids, which we know from our previous lessons must be related back to the chemical interactions that are found within the sample of the liquid. And so liquids are characterized largely by being molecular. They consist of molecules that are held in place by various non-covalent interactions, dispersion-type interactions, so that the forces between those molecules are relatively small compared to the kinetic energy of the molecules, so that the molecules interact transiently, but they can move around. They can take on new shapes, they form new intermolecular interactions, they find a new partner, and so they're fluid. We describe liquids as being fluid. So there are still interactions that are strong enough to keep the molecules together. They don't just escape into the atmosphere, but they're not as strong as the interactions between molecules or between atoms within a solid. And then the final state of matter, of course, is a gas, and we have gaseous fuels as well. For example, hydrogen gas is a famous gaseous fuel. It's the fuel often used to run rockets. The space shuttle ran on hydrogen gas. Engines that are powered by hydrogen were developed in large part for space exploration. Gases, of course, are even more amorphous than liquids or solids. They don't have a fixed volume per se. Instead, they have only very fleeting interactions between molecules. They consist of unique molecules that only very transiently interact with each other via collisions. But the intermolecular forces between the molecules are too weak to really make the gas molecules stay together. So gas molecules, for example, can escape into the atmosphere. One breaks away, doesn't have intermolecular forces anymore with the rest of the collection, and then he's gone. So gases move about randomly at speeds much faster than liquids, and they can take the shape of whatever container you put them into. They don't have defined volumes. So as you see, we have and we know already examples of fuels that are solids, liquids, and gases. And as we'll see as we continue through these lessons, determining the right fuel for a particular application will depend on the demands of that application, very much the energetic and the engineering constraints of what you're actually trying to do. Things like cost or weight, or how long the fuel needs to be stored before it's going to be used to power something. So in general, what determines whether a fuel is a solid, a liquid, or a gas? You know this already from your introduction to structures of molecules and interactions between molecules. The answer is really about bonding and intermolecular forces. It's those chemical bonds and those transient intermolecular interactions that determine whether something is a solid, liquid, or gas. It's about how much energy has to be put into the system in order to overcome those interactions and free or liberate a molecule from either a solid or a liquid, or in the case of a gas, it's already been liberated. So this is something we're going to come back to again and again in this course, this idea of intermolecular forces as defining structural properties and other types of physical properties. So you'll see this coming up in the problems associated with this lesson. It's worth remembering that strong intermolecular forces lead to higher boiling points and can even make things solids. So the explanation for why something is a solid as opposed to a liquid is usually stronger intermolecular forces, or liquid relative to gas. So at this point, it's a good place to take a break, to solve some of the problems associated with this unit. Make sure that you really understand the difference between a chemical and a physical change, and that you're starting to build your sort of library of examples of what a fuel is and examples of reactions that fuels undergo. Because in the next few lessons, we're going to start talking specifically about the chemical reactions that fuels undergo in a sort of way that chemists talk about chemical reactions.